Welcome to section 3.5, rational functions. Objective number 1, find the domains of rational functions. So a rational function is a function of the form f of x equals p of x divided by q of x, where p of x and q of x are polynomial functions and q of x does not equal 0. One of the simplest rational functions is the reciprocal function, which is f of x equals 1 over x. The domain of a rational function is the set of all real numbers except the x values that make the denominator 0. We can express the domain in set builder or interval notation. For instance, f of x equals this polynomial, x squared plus 7x plus 9 over x times x minus 1 times x plus 5. This function in the numerator is the p of x, and the function in the denominator is the q of x. Now the domain is going to be the set of all real numbers except 0, 2, and negative 5, because those values make our denominator 0. And if our denominator is 0, then our function is undefined. So in set builder notation, we would write this as all values of x except for when x equals 0, x equals 2, and x equals negative 5. In interval notation, we would write this as negative infinity to negative 5, negative 5 to 0, 0 to 2, and 2 to infinity. Okay? In these examples, we're asked to find the domain of each rational function and write the answer in set builder and interval notation. So all of these are rational functions. So the exception or restriction is going to be the x values that would make our denominator 0. So we know x minus 5 cannot equal 0. So that means x cannot equal 5. So our domain will be all x values where x does not equal 5, or in interval notation, it would be negative infinity to 5, union 5 to infinity. For b, we have g of x, and its denominator is x squared minus 25. This expression cannot equal 0, so then x squared cannot equal 25, which means x cannot equal plus or minus 5. So our domain will be all x values except for when x equals 5 or x equals negative 5. So interval notation would be from negative infinity to negative 5, union negative 5 to 5, union 5 to infinity. Now for c, h of x, our denominator is x squared plus 25. So this is similar to b, except for we have a positive 25 instead of a negative. So we know our denominator can equal 0, which means our denominator cannot equal negative 25. Taking the square root of both sides, we are then going to get plus or minus 5i. Now, 5i is not a real number, so our domain is going to be all x values, or in interval notation, negative infinity to infinity. Okay, so for c specifically, no real numbers cause the denominator of h of x to equal 0. Therefore, h of x's domain is going to consist of all real numbers. All right, objective 3, identify vertical asymptotes. So the line x equals a is a vertical asymptote of the graph of f of x if graph of a function f if f of x approaches infinity or negative infinity as x approaches a from either side. So a rational function may have no vertical asymptotes, one vertical asymptote, or several vertical asymptotes. The graph of a rational function never intersects a vertical asymptote, so we'll use dashed lines to show the asymptotes on the graph. The line is a vertical asymptote of the graph of a function f if f increases or decreases without bound as x approaches a. So we have 4 examples here that give a synopsis of what your rational function could look like as it's approaching a vertical asymptote. So as x approaches a from the right-hand side, f of x approaches infinity, and this looks something like this on the graph. Okay, so I'm approaching my vertical asymptote a from the right-hand side, and my y is going to infinity. Now I can approach my vertical asymptote from the left, and my y going to infinity will look something like this. So I'm approaching the line, never going to cross it. The next one, as x approaches a from the right, my y is decreasing. And as x approaches a from the left, my f of x is decreasing. Okay? So if the graph of a rational function has vertical asymptotes, they can be located using the following theorem. If f of x equals p of x divided by q of x is a rational function in which p of x and q of x have no common factors other than 1, then a is a 0 of q of x, the denominator. Then x equals a is a vertical asymptote of the graph of f. A value where the denominator of a rational function is 0 does not necessarily result in a vertical asymptote. So if the value of a causes the denominator to be 0, but there is a reduced form of the function's equation in which a does not cause the denominator to be a 0, then there is a hole. For instance, say we have the function here f of x equals x squared minus 4 divided by x minus 2. Our denominator here is x minus 2, which would tell us that 2 is going to be excluded from the domain. However, because we can write f of x in reduced form, meaning when we take f of x and we put it as a product of linear factors, we see that the numerator and denominator both have a common factor, x minus 2. Since they have a common factor, we can simplify f of x, which then just gives us x plus 2. Now, the common factor that was eliminated is going to actually represent a whole. Okay, so the x minus 2 is going to represent the whole in the graph. All right, so when you have common factors, that linear factor represents the whole. However, if you just have linear factors in your denominator where there are no common factors, then those linear factors represent the values that make f of x undefined. Okay. Now, take note that your graphing calculator may not show the holes in your graph, so this is something that you're going to have to verify by hand. So in these examples, we're asked to identify the vertical asymptotes. So for all of these, we're going to first put our f of x as a product of linear factors, and then we are going to identify our asymptote. So if we take f of x and rewrite this in factor form, we'll have x minus 3 in the numerator, and then this quadratic is going to simplify to the factors x minus 5 and x plus 1. So we have no common factors in the numerator and denominator, so we can set our factors in the denominator to 0, right, giving us our vertical asymptotes, x equals 5 and x equals negative 1. Okay. All right, B. We're going to rewrite f of x as a product of linear factors in the denominator, and that will be x plus 7 and x minus 3. Okay, so we have common factors in the numerator and denominator, so this would simplify to 1 over x minus 3. Okay, so we would then set our denominator to 0, x minus 3, which gives us the vertical asymptote x equals 3. Okay, now x plus 7 would be the linear factor of our 0. So we would have a linear factor when x equals negative 7. Okay. To find the actual point, we would then plug negative 7 into our table to get the y. Not into our table, into our function to get the y. Alrighty. C, f of x equals negative 8 over x squared plus 25. So this cannot be factored. So we would then take our denominator and set it equal to 0. So we get x squared equals negative 25. So x equals plus or minus the square root of negative 25. So x equals plus or minus 5i. So this is not a real value. So since the denominator has no real zeros, f of x then has no vertical asymptote. Okay. All right, here's a checkpoint. So why don't you pause and attempt this checkpoint. Identify the vertical asymptote of f of x. All right, you should have gotten a vertical asymptote at x equals negative 1. Objective 4, identify horizontal asymptotes. So the line y equals b is going to be our horizontal asymptote of the graph of the function f if f of x approaches b as x approaches infinity or negative infinity. So as x is approaching infinity, f of x then is going to be approaching d. Okay, so that would be either above the asymptote or below. Okay. Now, as x is approaching negative infinity, f of x is approaching d. So again, we could have it below or we can have it above. Okay, so recall that a rational function may have several vertical asymptotes. By contrast, it can have at most one horizontal asymptote. Although a graph can never intersect a vertical asymptote, it can cross a horizontal asymptote. It won't cross it all the time, but it is possible. So if the graph of a rational function has a horizontal asymptote, it can be located using the following theorem. So we're going to let f be a rational function defined by f of x. Remember, f of x is p of x over q of x, so a polynomial in the numerator, polynomial in the denominator, where n is going to be the degree of the numerator and m is going to be the degree of the denominator. And you use n and m to determine what your horizontal asymptote is for your rational function. So for the first one, if n is less than m, then the x-axis, or y equals 0, is the horizontal asymptote of the graph of f. If n equals m, then your horizontal asymptote is going to be the line y equals a sub n divided by b sub m. Now these values represent the leading coefficients of your numerator and your denominator. So they're located right here. Okay. And lastly, if n is greater than m, then the graph of f has no horizontal asymptote. So if it's less than m, then the x-axis is your horizontal. If n equals m, then y equals your leading coefficient in the numerator divided by the leading coefficient in your denominator. And if n is greater than m, then there's no horizontal asymptote. So in these examples, let's now find the horizontal asymptote. Okay. So for f of x, our n is going to represent the degree of p of x, and our m is going to represent the degree of q of x. So the degree of p of x is 1, the degree of q of x is 2. 1 is less than 2, so that means n is less than m. So this means that our horizontal asymptote is going to be the x-axis, or the line y equals 0. All right, let's do the next one. In this function, our n is going to be 2, and our m is going to be 2. So 2 equals 2, which means n equals m. So our equation for our horizontal asymptote is going to be the leading coefficients in the numerator divided by the one in the denominator, which equals 3. So our horizontal asymptote is going to be the line y equals 3. Okay. And C. Our n, which is the degree of the polynomial in the numerator, which is 3, and m, which is the degree of the polynomial in the denominator, which is 2. So n is greater than m because 3 is greater than 2. So that means we do not have a horizontal asymptote for this function. Okay. All right, it's your turn. Checkpoint time. So identify the vertical asymptote for this function. Oh, actually, sorry. Identify the horizontal asymptote for this function. All right. So the horizontal asymptote that you should have gotten is the equation y equals 2. Objective 5. Use transformations to graph rational functions. So some rational functions can be graphed using transformations like the horizontal shifting, vertical shifting, shrinking, stretching, reflecting of the common graphs f of x equals 1 over x or f of x equals 1 over x squared. For example, if we were given the function f of x equals 1 over x minus 3 minus 1, we could use transformations to graph this function. So right off the bat, I know that my parent function is 1 over x. And I see here, I shift to the right 3, and I shift downward 1. Okay. I also notice from this graph that I have a vertical asymptote at x equals 3, and I have a horizontal asymptote at y equals -1. Okay, so I'll have my horizontal asymptote and then my vertical asymptote. So you can plug in points to get, or plug in values of x to get your y, which will give you points to plot on your graph, or you can utilize your calculator. Okay, so here are some points. I'm just going to do a rough sketch of our graph. All right. All right, objective 2. So the arrow notation used throughout our discussion of reciprocal function is summarized in the following box. So we've seen this before, but just to make sure that we've given it some context, x approaches a to the power the plus sign, this means that x is approaching a from the right. So when you see a plus sign, it means from the right. When you see a negative, it means from the left, but will not equal a. Okay? So remember, for asymptotes, we're always approaching it, but we will never equal it. And then a approaching infinity or negative infinity would use the infinity and negative infinity signs. Okay? So now we can take that and apply it to this function f of x and complete these statements. So as x is approaching infinity, so as x is getting bigger, f of x or y is going to be approaching 1. Okay, so it's right here. All right, as x goes to infinity, our graph is going towards that horizontal asymptote. As x is approaching negative infinity, okay, our y or f of x is also approaching 1. Okay. Now, as x is approaching 3, so that's our vertical asymptote, from the right-hand side, f of x is approaching infinity. And as x is approaching 3 from the left-hand side, f of x is approaching negative infinity. Okay, so it's going this way. All right. Objective 6. So now we're going to graph rational functions, and here's a strategy for doing so. This strategy can be used to graph f of x in the form p of x divided by q of x, where p and q are polynomial functions with no common factors. So first we're going to determine whether the graph of f has symmetry. So if f is symmetric to the y-axis, and we'll test whether it's symmetric to the origin. Then we'll find our y-intercepts, and we'll do that by substituting 0 for x. Next, we'll find our x-intercepts, and this is setting the equation p of x to 0. Then we'll find the vertical asymptotes by setting q of x equal to 0. Then we'll look at the horizontal asymptotes by looking at the degrees of p of x and q of x. And then we'll plot points, all of the points actually, between and beyond each x-intercept and vertical asymptote in order to get an accurate representation. I would definitely encourage you to utilize your calculator and the table to get points so that you can graph a beautiful function. All right, so now let's graph this function. We're going to go through the steps. So first off, we know that the numerator is our p of x and the denominator is our q of x. So the first thing is we need to test for symmetry. So we'll first take f of negative x. So we'll substitute negative x in for x. And simplify. So we have x squared plus x minus 6, and then x squared plus 5x minus 6. This does not equal f of x. Then we'll test negative f of x. X squared minus x minus 6 over x squared minus 5x minus 6. And we'd have negative x squared plus x plus 6 over x squared minus 5x minus 6. And this does not equal f of negative x. So that means our function, the graph, has neither y-axis or origin symmetry. So it's neither even nor odd. All right, step 2. Find the y-intercept. To find the y-intercept, we're going to substitute 0 for x. So f of 0 equals 0 squared minus 0 minus 6 divided by 0 squared minus 5 times 0 minus 6, which equals negative 6 over negative 6, which equals 1. So this gives us the point 0, 1. Okay. Step 3, we'll find the x-intercepts. To find the x-intercepts, we're going to set p of x equal to 0, and p of x is our numerator. So x squared minus x minus 6 equals 0. We'll put this in factored form. So that would be x minus 3 and x plus 2. Then we'll set each of these factors equal to 0, and we'll get x equals 3 and x equals negative 2, which gives us the points 3, 0 and negative 2, 0. Step 4, we'll find the vertical asymptote. So that's taking q of x and setting it equal to 0. So that's x squared minus 5x minus 6, because that's the polynomial in the denominator. Placing this in factored form, we will get x minus 6 and x plus 1. Setting each linear factor to 0, we then get our vertical asymptotes, x equals 6 and x equals negative 1. And lastly, our horizontal asymptote. So the degree of the numerator is 2, the degree of the denominator is 2, 2 equals 2, so n equals m. That means the horizontal asymptote is going to be the leading coefficients, which are 1 divided by 1, which equals 1. So the horizontal asymptote is y equals 1. Okay, so we can graph this, and our units are going 2, 4, 6, 8, 10, so it's going by 2. So let's draw our vertical asymptotes first. So we have 6, and then we have negative 1. And then we have y equals 1. Then we'll plot our intercepts, so 0, 1. We have 3, 0, 2, 4, 6. So 2, 4, so it'll be right here, 3, 0. And negative 2, 0. So the next thing I would do is go into my calculator and get some points. So I'll plot some here for us. So there's one here. And then we have one here, one here, and one here. Okay. And then we can sketch our graph. Remember, we're not crossing the asymptotes. We're approaching. Now our graph does cross the horizontal, which we know is possible, but it does not cross the verticals. Okay. All right, let's do another one. I'm going to change up the color. All right, so we have p of x and we have q of x. The first thing we're going to do is test for symmetry. So f of negative x is the first one. So 2 times negative x squared over negative x squared minus 4, which equals 2x squared over x squared minus 4. This does equal f of x. So that means the graph is symmetric to the y-axis. So that will help us in plotting points. Okay. Step 2, we can find our y-intercept. We do that by substituting 0 in for x. So f of 0 equals 2 times 0 squared over 0 squared minus 4, which equals 0 over negative 4, which equals 0. So that gives us the point 0, 0, which is the origin. So for the x-intercept, we are going to set p of x equal to 0. P of x is the numerator. So 2x squared equals 0. So x squared equals 0. So x equals 0, which gives us the point 0, 0. Now we find our vertical asymptote by setting q of x equal to 0. And we have x squared minus 4 equals 0. This is the difference of squares, so we'll have x minus 2, x plus 2 equals 0. So x minus 2 equals 0 gives us x equals 2, and x plus 2 equals 0 gives us x minus 2. So those are our vertical asymptotes. Then our horizontal asymptote, we look at our degrees. So n equals 2, m equals 2, 2 equals 2, so m equals m. So y is going to be 2 divided by 1. So y will equal 2, which is the horizontal asymptote. Okay, so let's plot our asymptotes. So we have y equals 2. And we have x equals 2. And x equals negative 2. We have 0, 0, and no other points. So we would definitely have to use our calculator to get some other points. So I'll plot some here for us. So we have this one and this one. And then we have this one, this one, and then the replica on the other side. Okay. All right. So that's my rough sketch of f of x. Okay, let's graph one more. C. All right. So 2x squared minus 8x is our p of x. And then x minus 3 is our q of x. So first we want to test symmetry. So f of negative x. So 2 times negative x squared minus 8 times negative x plus 8 over negative x minus 3. That gets me 2x squared plus 8x plus 8 over negative x minus 3. So we know that this does not equal f of x. So we'll test the next one, which is subtracting, or I guess not subtracting, multiplying our numerator by negative 1. So we'll get negative 2x squared plus 8x minus 8 over x minus 3. And this does not equal f of negative x. So the graph has neither y-axis or origin symmetry. Okay. So next is the y-intercept. So that's f of 0. So f of 0 equals 2, 0 squared minus 8 times 0 plus 8 over 0 minus 3, which is 8 over 3, which gives us the point 0, 8 over 3. Our x-intercept is p of x equals 0. So that's 2x squared minus 8x plus 8 equals 0. I can factor out a 2 to get my quadratic in more easier terms. So this will give me 2 times x minus 2, x minus 2. So x minus 2 equals 0, x equals 2, which gives me the point 2, 0. For my vertical asymptote, so that's q of x equals 0. So x minus 3 equals 0. So then x equals 3 is my vertical asymptote. And then 5 is my horizontal asymptote. N equals 2, m equals 1, n is greater than m because 2 is greater than 1. So my horizontal is not applicable to this problem. So I just have a vertical asymptote at x equals 3. Okay. So I'm going to plot my x-intercept, which is 2, 0, and my y-intercept, which is 8 over 3. Okay. And then I'm going to plot some other points here that I found on my calculator. There we go. All right. So that's what your graph should look like. Now, if you are like me, you would notice that my graph seems to have some sort of reflection over this slanted line. All right. And that leads us into our last asymptote that we're going to look at, which is called the slant asymptote. So a rational function will have a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. So to find an equation of a slant asymptote, we're going to divide the numerator of the function by the denominator. The quotient will be linear, and the slant asymptote will be of the form y equals the quotient. So in our first example here, where we're asked to determine the slant asymptote, let's first verify that we actually have a slant asymptote. So n is the degree of the numerator, which is 3, and m is the degree of the denominator, which is 2. Now, in order for there to be a slant asymptote, n must equal m plus 1. So 3 must equal 2 plus 1, which it does. So I know a slant asymptote exists. So now I can perform my division. So I have 3x cubed plus 0x squared plus 0x plus 0. Those are the missing powers. So dividing 3x cubed by x squared, I'm going to get 3x. Multiplying 3x by each term in the dividend, I'm going to get 3x cubed minus 27x. And let's put that over its correct term. Okay. So now I'm going to subtract, and I'll get negative 27x. So negative 27x is the remainder, and 3x is the quotient. Now my slant asymptote is going to be equal to y equals the quotient. So that means my slant asymptote is going to be the line y equals 3x. Okay. Let's do B. All right, let's check. So n here equals 2 and m equals 1. So we know n must equal m plus 1. So 2 must equal 1 plus 1, which it does. So a slant asymptote exists. Now we can perform division, and since this is a binomial, we can actually use synthetic division. So we have 2 minus 5 and 7. Bring on the 2, multiply, add, multiply, and add. So 5 here is the remainder, and 2 and negative 1 is our depressed polynomial, which is 2x minus 1, and that is our slant asymptote. Okay. All right, our last objective focuses on solving applied problems involving rational functions. Okay. So Young's rule is a formula for calculating the approximate dosage for a child given the adult dosage. For an adult dosage of d milligrams, the child's dosage, C of x, can be calculated by this formula. C of x equals d times x divided by x plus 12, where x is the child's age in years and x is greater than or equal to 2 and less than 13. We have 3 questions that we need to answer. Okay. The first question, what is the horizontal asymptote of the function, and what does it mean in the context of this problem? Well, to find the horizontal asymptote, we're going to look at the degree of the numerator and denominator. They are both 1. So n equals m because 1 equals 1. So we're going to take the leading coefficient in the numerator, which is d, and the leading coefficient in the denominator, which is 1. So y equals d. So our horizontal asymptote is y equals d. Now what does this mean? Well, we know d represents the adult dosage. So the child dose will approach the adult dose but will never equal it. All right? So you're either a child dose or an adult dose. You can't be a child and adult dose. Makes sense, especially when it comes to medication. All right, B, what is the vertical asymptote? Well, to find the vertical asymptote, we are going to set q of x equal to 0. Now, q of x is the polynomial in the denominator. So x 12 equals 0, and so x equals negative 12. So the vertical asymptote is x equals negative 12. Okay. And for an adult dosage of 50 milligrams, what is the approximate dosage for a 9-year-old child? Well, an adult dose is 50 milligrams, so that means D equals 50. So C of x will equal 50x divided by x plus 12. X represents the child's age, and our child here is 9. So we are going to substitute 9 into our function, and we will get approximately 21.4 milligrams. Okay. All right. Next, a company is planning to manufacture wheelchairs that are light, fast, and beautiful. The fixed monthly cost will be $500,000, and it will cost $400 to produce each radically innovative chair. A, we're asked to write the costing function C of producing X wheelchairs. B, write the average cost C hat of producing X wheelchairs. Then find and interpret C hat at 1,000, 10,000, and 100,000 for C. And then D, what is the horizontal asymptote for the graph of the average cost function C hat, and describe what this represents for the company. So let's first do A, where we need to find the cost function. So the cost function is going to be how much each wheelchair costs plus the fixed monthly cost. Okay. The average cost is going to be C hat, and that's going to be the total cost for making the wheelchair divided by the number of wheelchairs. So if we wanted to find C hat of 1,000, 10,000, and 100,000, we would substitute in these values for X and simplify. Okay, and we would repeat that process. When we repeat that process, we get 900, 450, and 405. Now, what do these mean? Well, these represent the average cost per wheelchair of producing X wheelchairs per month is C hat of X. In other words, if I were to take the first one when we plugged in 1,000, the average cost per wheelchair of producing 1,000 wheelchairs per month is $900. The average cost per wheelchair of producing 10,000 wheelchairs per month is $450. The average cost per wheelchair of producing 100,000 wheelchairs per month is $405. Okay. And lastly, here we have D. Now, D asks us to identify what the horizontal asymptote for the graph of the average cost function C hat would be, and then describe what it represents for the company. Okay, so to find the horizontal asymptote, we need N and M. So N is going to be 1, M is going to be 1. So N equals M because 1 equals 1. So Y is going to be 400 over 1, which is just 400. Okay. So our horizontal asymptote is going to be Y equals 400. But what does that mean for the company? Well, it means that the cost per wheelchair approaches 400, as more wheelchairs are produced. So the value will never cross 400, but it will continuously approach 400. Okay, because we automatically know from the problem that it takes $400 to produce a wheelchair. Okay, alone. So the average cost will approach 400, but it will never cross it or never equal 400. All right, great. And that concludes section 3.5.